Okay, so moving on now, we've got a brand new topic. This is applying differential calculus, okay? And it is as it sounds. It's basically taking everything that we've done from differentiation and applying it to a context. We've already looked at it in one context in terms of gradient, and that's going to be important for what we need to move on to, because what we're doing when we're finding a gradient is we're looking at specific values within a function, okay? So what we're going to do now is we're going to look at different real-life contexts where that can be useful. Okay, and basically what we're doing is we're trying to find where it's maximum, where it's minimum, where it's highest, where it's lowest, and so on and so forth. And if you think about it, there's a lot of different situations where that would be useful. So one of the ones we look at most often is in terms of optimizing, and that's a word you'll use quite a lot, optimizing the shape of something. Okay, so when the dimensions change within that shape, for example, if it was a 3D shape, if the dimensions change, then the overall volume and the overall surface area, they'll change as well. So is there an optimal value for the dimensions that optimizes the overall volume? Okay, is there an optimal dimension that optimizes or maximizes the amount of surface area that we have? Different companies are going to want different things. If it's, for example, a box of cereal, perhaps the company want a higher surface area so that they can advertise more. Perhaps they just want to maximize the volume so that they can fit in as much cereal, in this case, as possible. Okay. It's also used quite a lot in terms of profit and loss. Okay, so if a company can see or can graph their profit and loss, then we can look at specific values within that are obviously going to maximize something. Okay, an example used quite a lot, and that example that we actually used in National 5 was optimizing the actual cost of a magazine. Okay, so obviously the higher the magazine is in cost, then perhaps at least past a point, the lower the overall profit will be. Okay, and vice versa. If it's too low in cost, then they're not going to make any profit. So is there a maximum? Is there an optimum cost of that magazine that will lead us to the maximum profit? Okay. So lots of different real life examples, and that's going to be the difficulty, I think, with this topic, is the fact that in a test, it's not going to necessarily say anything about differentiation, but what it will say is something along the lines of optimizing or maximizing and minimizing. Okay. And from what you've seen already, if we want to try and find a maximum and minimum value, which is exactly what we're doing when we're finding stationary points, okay, then we have to use differentiation. But this is just obviously starting with a context as opposed to starting with a graph. There may be a graph involved. If it's a function, then there obviously will be. But in terms of actually finding those maximum and minimum values, you don't necessarily have to draw out the full graph, okay? Right, so this is an example that's used quite a lot. We're not going to spend too much time looking at it, but it's basically what we've got here is we've got a value x. Okay, what's the idea of this is this is a net of a shape. We're going to fold it up to make a cuboid. And by changing obviously that value x is going to change the overall volume of the cuboid, and it's also obviously going to change the wastage. If you imagine how this folds up, you basically cut these corners out, you cut the squares out in the corner, you chuck them away, and then you'd fold up what's left to make a cuboid. Okay, so there's a balance to be struck here. And as I say, we're not going to look at this in too much detail, but you can start to see the idea of optimizing. Okay, the more obviously the higher x is, the more wastage there's going to be, but could that actually change the overall volume that we're dealing with at the end of it all? Okay, so if a box was being built by a company, if a box was being built, then a company would need to consider the dimensions it would take to maximize the overall volume from the material needed to make it. As x is increased, the amount of wastage probably increases, but the volume of the eventual box increases too, to a point at least. Okay, there's lots of things to consider here, most notably this last bit. So what this is a kind of an interval for which x can take. So it wouldn't necessarily, and the question is going to be based around stuff like this, it wouldn't necessarily tell you this interval. But you can look at this and you can establish that x has to be greater than 0 and x has to be less than 1. Okay, so if you want, pause this and have a think to yourself for a while. Okay, I know most of you won't, you'll just let it run, but nonetheless, okay. The idea is if x was 0, then this would just be a rectangle, in which case it couldn't actually then make a cuboid. Okay, if x was 1, then if you notice the dimensions here, then this dimension here, okay, this would be 1, in which case it would be 1 on the other side, in which case you'd cut off basically what we call the flap, the bit that you fold up to actually make the cuboid. Okay, so anything, if x was 1 or anything bigger than 1, then again you just have a rectangle. So the values are 0 and 1, you just end up with a rectangle. Anything in between, you'd have this cuboid net, and then it would work. So there's little things like that that have to be considered as well in terms of the interval of the x values that we can take. What that means in terms of a graph, because obviously a lot of these graphs are infinite. Okay, all these graphs are infinite. And obviously at the very extremities of those graphs, you're probably going to have your maximum and your minimum. So we only want to look at it on a certain interval. Okay, so that needs to be taken into account as well. A lot of the time, the question will tell you that interval, but sometimes in a situation like this, you might be able to work it out, and you do have to work it out to be able to consider it. Okay. So the point is, you can look at the graph for all of this, okay, and you can pretty much just take this in exactly the same way as we took the questions from differentiation the first time around. Okay, you draw the graph, you look at the interval, and you work out where you have your highest values and your lowest values, and then you kind of just match it up with the question. Okay, or you can just go through and you can use differentiation. So for example, for this one, we can either look at the graph of a function. Okay, so the idea here is we could obtain a function, we could obtain an expression for the volume of this this eventual cuboid. Okay, and then we could draw the graph of x against the volume. Okay, that sounds a bit confusing, but you'll see some examples in this in a second. So you can draw the graph from scratch, and you can just literally work out every single point, or obviously you can use differentiation in the same way that we did before to find the kind of the main points of interest. We don't want to necessarily draw this whole thing out, but if we find the points of interest, in other words, where it changes from kind of increasing to decreasing, then we can obviously find a maximum turning point and a minimum turning point. If you remember from before, the maximum turning point and the minimum turning point are not necessarily the highest and the lowest values. And that's where the kind of the actual interval comes in, because we check what's happening at the end of the interval. Okay, but all of that will allow us to determine the best possible scenario. And I've written it like that because we want maybe to minimize the wastage, we maybe want to maximize the volume. It all depends on the question, and it's going to be all the more important to read that question carefully. Okay. Right, so just starting off with graphs just now, just to get us used to this, but dealing with a specific function. Right, this function could be to do with anything. Okay, this could be the function that we get for the area of something. Okay, it could be to do with profit and loss. It doesn't necessarily matter at this stage. I just want to think about the maximum and the minimum values and the stationary points within that, and how the interval kind of changes around that, giving us the different highest and lowest or maximum and minimum values. Okay, so this is the graph of the function. That's what that function looks like. X minus 3 squared plus 2. We knew we'd have a turning point of 3, 2. It's positive, so it's a smiley face, so it goes up the way. So that's what that looks like. Okay, we've obviously got lots of different values within that. Okay, and you can see if we're kind of dealing with the whole thing, this is of the interval between -1 and approximately 7. But this graph is infinite. These lines go on forever and ever and ever, up that direction and up that direction, forever and ever and ever. Okay. So this is dealing with a specific interval, and as I say, more often than not, you would be dealing with a specific interval. Okay. What I've done here is I've chosen a specific interval, even within that interval. Okay. So we've got this interval between where x is between 0 and 4. Okay. So x can equal 0 at this point here, and x can equal 4 at this point here. So we're just focused on this bit, this green line here. Okay. So that's the specific interval that we want to focus on. And we can see, because we have the graph, we can see that the minimum value is 2. So the lowest value, the lowest point on this graph is 2, or occurs when x is 3, okay? And the minimum value is actually 2. And we can see that the maximum value is 11, and that occurs when x equals 0. So having the graph there in front of us, it's very easy to see where the maximum and minimum values are in an interval as well, okay? But we're not always necessarily going to have that. Okay, we can draw it, and we can take the graph and we can use it to find the maximum and minimum values. Obviously, that's going to take a little bit of work though, and generally we're going to have more complicated functions in this. Okay. Right, if we did not have the graph, we would have to substitute in the end values of the interval into the equation and also look for stationary points. So that's kind of what we're dealing with here. If we take this graph away entirely, and this is all you have the function and you have this interval, then you'd have to differentiate, in which case you'd find the minimum turning point, and then you'd have to substitute in the two end values of the limit, and you would find out what happens in there. And you would see that the lowest value would be that stationary point, and then the highest value would actually occur when x is 0. Okay, so you've got two options there: draw the graph, or you can just do it through algebra and differentiation. Right, one point that I wanted to make at this stage though is that if the interval was changed, so this is a specific interval, don't know what it's for, but it's an interval that we're dealing with in this question. If we were to change that interval, in other words, we were to deal with this interval here, perhaps between 4 and approximately 7, I think that's lines in the wrong place, but it doesn't really matter. The point is, with this interval, we can see that the maximum and minimum values are different to the interval that we had before. The minimum value is now here, okay, which occurs at 4, and it's approximately 2 point something, okay, and the maximum value occurs just before 7, okay, and it's approximately 15, 16. Point I want to make, as I say, in that same function, we can have different maximums and minimums, and they all depend on the interval. So this is very, very important to consider the interval, okay? Right. Generally, what I want to do, or what we want to do, is use differentiation. Differentiation is going to be much easier to actually find our maximum and minimum values rather than drawing this all out. You'll hate drawing graphs anyway, so we want to try and avoid that as much as possible, okay? But it's just a couple of things that we need to look at. We need to think about our maximum and minimum turning points, which we find through differentiation. And we need to think about the ends of the interval because the maximum and minimum values are not necessarily the minimum values or the maximum values within the interval. Okay, right. So an example, the function, and this is not necessarily a context just now, okay, but this is just kind of building you up to that point. So we've got a function f of x equal to 2x cubed minus 5x squared minus 4x plus 3. Within that function, we want to find the greatest and the least values, but only in the interval between where x is between -1 and 4. So x can equal -1 and it can go as high as 4, and then anything in between, but nothing out with that function, okay? So we can draw it, and basically what the work that we're going to do will allow us to draw it, but we don't necessarily need to get to that stage. I'm going to finish with the actual drawing of this function, but it's just to kind of give you an idea of what's happening. But we basically, by looking at that, I have no idea where the maximum and minimum values are, especially not on that interval. Okay, so we have to kind of use all our algebraic knowledge to find those things. So the first thing you want to do is you want to find your stationary points. And if you find your stationary points, then we need to differentiate. So we're going to take our f of x and we're going to find f dash x. Okay, so remember, obviously, we're coming back and forth between differentiation and integration now. So make sure you pick the right method. So differentiation means we take our power and we multiply it and then drop it by 1. So 6x squared minus 10x minus 4, the 3 disappears. Okay. Right, if we're going to find the stationary points, then we know the stationary points occur when the derivative is equal to 0. Okay, so write down your little line, however you remember it, 4 SPs, f dash x, I missed that out there, f dash x should equal 0, in which case 6x squared minus 10x, what we found as our f dash x, our derivative, is equal to 0. Now we have an equation that we can solve. Okay, and if you've got something like this and it's a quadratic, then you want to get it all equal to 0, which it already is. So keep it where it is. Don't start moving the 4 over or anything stupid like that, but factorize. Okay, right, that's it fully factorized. The 2 disappears, but that's it fully factorized, in which case we take our 2 brackets and they're equal to 0. If 3x plus 1 equals 0, then 3x equals -1, in which case 1x equals -1 over 3. And for the second bracket, x minus 2 equals 0, in which case x equals 2. So they're the 2 x values where we have stationary points. But remember what we're trying to do, we're trying to find overall where what the greatest and least values are. Okay, this is not what they are, this is just where they actually happen. So we need to go one step further and we need to substitute them in to our original function to find out where what they actually equal at those points. So when x is minus a third, so just basically taking all your x's out in the first instance, substituting in minus a third, stick it in your calculator or just work it through. Either way, you get 100 over 27, which is 3 and 19/27. Don't have to do much more with that, so don't panic. But that is obviously a value when x is minus a third, and we know that's basically a turning point. But again, at this point, we don't know if that's the biggest value or the minimum value. We don't know what kind of turning point this is, so we're going to have to do that as well. Okay, but do the same with 2. When x is 2, then f of x equals -9, in which case the y value is -9. Right, that tells us, and all it tells us is that there are stationary points at those 2 values. So when x is minus a third, we have a value of 3 and 19/27. Okay, and that's some form of turning point. It could be maximum, it could be minimum. You can kind of look at these and work it out, but try not to rely on that too much. And then there's another turning point at 2 minus 9. Okay. So now what we want to do is we want to take those stationary points and we want to determine their nature. So we need a nature table, okay? Minus a third and 2. We know obviously when x equals those values, then dy by dx equals 0. That's the whole process we just did, in which case the shape is flat, okay, turning points. And then we want to look at what's happening either side to determine whether they're maximum or minimum. Okay, so we're going to pick a number that's less than minus a third. We're going to pick a number that's between, that's completely wrong, between minus a third and 2, and then we want to pick a number that's greater than 2. Okay, so I'm going to pick for something that's less than minus a third. Obviously, minus a third is not quite -1, so I can pick -1. Okay, and I'm going to substitute that into dy by dx. Remember to pick the right one. This is why we draw our nature table, so we know what we're doing. So the -1 goes into dy by dx. we look at the value. All we're interested in is whether it's positive or negative. This is positive, okay? So we take that positive, we pop it in our table, okay? Telling us basically that the shape is increasing before it gets to the first stationary point, okay? So again, it gives us an idea of what's going to happen, but we need to keep going and we need to find out exactly what's happening. So we want a value between minus a third and 2, okay? Ignore that a second, but it's the same idea, between minus a third and 2. We can pick 0, okay? 0 is between minus a third and 2, and we substitute into our derivative. Okay, this should be slightly easier. 6 times by 0 squared minus 10 times by 0 minus 4 is minus 4. As again, all we're focused on is the fact that it is minus. We take that minus and we pop it in our table. And that tells us that between, or basically after minus a third, then the graph starts going down again. Okay, in which case we can see clearly that when x is minus a third, we have a maximum turning point. Okay, but we want to find out exactly what's happening when x is 2. So again, we go back to our derivative. We pick a number bigger than 2. 3 is fine, 10 is fine, it depends what you're happy working with, but put it into your derivative. So 6 times by 3 squared minus 10 times by 3 minus 4 is 20. That is positive. Goes in our table. It tells us that after 2, the graph is increasing again. Okay, so we can see that at 2, whatever it was, I can't even remember, when x is 2, we have a minimum turning point. Okay, so there's a maximum turning point at minus a third, 3, 19, 27. So that's the maximum value and that's the minimum value. Okay. But it's not the overall maximum and minimum value, because either side of them, the graph is obviously increasing, decreasing. And you can see that kind of from the diagram here. This is going to go back up again. Although this is the minimum turning point, we're going to go back up again, and this point might reach a point that's higher than the maximum turning point, and then vice versa over here. This is going to come back down again, and this might get to a point that is lower than our minimum turning point. So what we need to look at now is we need to look at either end of the interval to find out whether that's true or not. So I'm going to take these turning points. I'm going to do a bit more work on them. Okay. So that's there just now. Actually, we're not going to do anything with the turning points, but we want to look, as I say, and the interval. So this is very, very important. This is not just there for banter. It's there for a reason. And we basically want to look at the interval and find out exactly what's happening there. So when x is minus 1, how big or how small is the overall function? Okay. In other words, what is the point? What is the overall coordinate at minus 1? So we take minus 1, replace it with our x's, and we get a value of 0. Okay, and we're going to do the same with 4. We're going to get an overall value of 35. Okay, so what we basically want to look at is, as we know at this first point, this is a maximum turning point. Okay, so we know it's going to get lower to the left of this point. Okay, so up until minus 1, it gets to 0. We want this point to be lower potentially than this point here, which it's not, telling us that this is the overall minimum value within that interval. Then vice versa with here, after the point 2, when x is 2, okay, it starts going up again. This is a minimum turning point. So then to the right of this, it starts increasing again. We want to basically see, is it within the kind of space that's left in the interval, does it get any higher than 3 and 19/27? And it does. So this point now becomes our maximum, greatest value within that interval. So if you were to draw the graph and plot these points on, okay, you would see what's happening here. Okay, so they're the 4 points that we found, and this is the interval that we're dealing with. We're starting here, we're starting where x is minus 1, okay, and we're ending where x is 4. So we can see the graph continues there as well, okay, but we're not interested in those values. They're not within our interval, but we're just trying to work out within this interval, where is the highest value and where is the lowest value. This is obviously the lowest value, but the maximum turning point is not the highest value within that interval. Okay, at the end of the interval, we have the point 435, so the highest value is there. In which case, we can now answer the question on the interval minus 1, x is between minus 1 and 4. The greatest value of f of x is 35, and the least value of f of x is minus 9. Very long-winded question. But the beauty of questions like this, you get a lot of marks. You've just got to make sure you answer the question at the end and you find out all these different points. It's not enough to just find a maximum turning point and a minimum turning point. You can see from this graph here that just because there's a maximum turning point, it doesn't mean it's the highest value on that function. Okay, so you have to look at either end of the interval.